series of work that I've been recently doing. The last paper is this one, where with two students we are trying to apply the methods of Newton-Cartan geometry to the problem of quantum Hall effect. And I will first, in my talk, give you a brief overview of the quantum Hall physics, and then talk about the symmetries of the problem. That would be the key for us to write down the effective Lagrangian and then derive the physical consequences from this approach. I must warn you that there is no holography yet in this talk, but it indicates that maybe there is a useful holographic way of understanding quantum Hall effect. So very briefly, let us remind ourselves about the Hall effect. The classical Hall effect is a very simple physics, undergraduate physics. If we have electron gas, let's imagine we have a two-dimensional electron gas in a magnetic field that is perpendicular to the board, and then we put in an electric field along, say, the x direction, then the electrons will move along the y direction, and the velocity of the motion of the electron can be computed by balancing the electric force and the Lorentz force. And from that you deduce the velocity of the electrons, and knowing the density you can find the current. And by dividing the electric field in the x direction by the current in the y direction, you determine the whole resistance rho xy, and you find that rho xy is proportional to the magnetic field if the density of electrons in the two-dimensional density of electron is held fixed. Now, the quantum Hall effect was observed in 1980, I believe, and the experiment was done on a sample that is at low temperature and it's very clean sample. And what was found is that the behavior of rho xy as a function of the magnetic field for this sample doesn't follow the linear prediction of the classical theory. In fact, it has various steps, quantum Hall plateau that correspond to sigma xy equal to an integer times the quantum Hall constant e squared over 2 pi h bar. That was explained very quickly by using the picture of simple non-interacting electrons in a magnetic field. We know that if we solve the Schrödinger equations in a magnetic field, then the eigenstates of an electron organize themselves into Landau levels. Imagine that we have a situation where we will have a chemical potential that lies between two Landau levels. Then we would feel all the electron below this chemical potential, and all the Landau levels above that chemical potential will be empty. If only these electrons contribute to the transport, then the density of these electrons will be proportional to the magnetic field, because the degeneracy factor of each Landau level is proportional to the magnetic flux. And therefore, from that you deduce that sigma xy should be proportional to the number, should be equal to that quantized Hall conductivity times the integer. Of course, this explanation doesn't tell you why extra electrons that are, if we change the magnetic field, some electron would be, some level would be partially filled or partially empty. In order to explain the quantum Hall plateau, we have to understand more the physics of disorders that is beyond the scope of this talk. The fractional quantum Hall effect is much more non-trivial phenomena, where if you go to even lower temperature and cleaner sample, you will discover plateaus which correspond to sigma xy equal to a fraction, a rational number times the quantum of conductivity. And let's think about a particular plateau, that is 1/3 plateau. In this case, we have only 1/3 the number of electrons compared to the degeneracy of the lowest Landau level. That means that if we are dealing with non-interacting electrons, then the ground state of the system would have a huge degeneracy, because there are many ways to put these electrons between the state on the lowest Landau level, and all these states have the same energy if the Hamiltonian is just the sum of one particle Hamiltonian. So somehow the fact that we have quantum Hall plateau at nu equal 1/3 tell us that the interaction between the electrons are very important for the physics. We now think that interaction somehow lift the degeneracy of the ground states. So instead of a huge number of states with the same energy, we have on a simple topology just one single ground state, and all the other excited states are separated from the ground state by a gap. So this would happen at particular value of the filling factors. For example, for nu equal 1/3 or nu equal 1/5, etc., we would have the situation where the system has a gap. So for this talk, the existence of a gap in a quantum Hall system will be the most important information about the quantum Hall system that we need. So a little bit more about the energy gap. In the integer quantum Hall effect, the energy gap is nothing but just the distance from one Landau level to the next Landau level. And that distance is proportional to B over m, where B is the magnetic field and m is the mass of the electron. So in reality, it would be the band mass of the conduction electrons. In the fractional quantum Hall system, there are two separate energy scales. One energy scale is the distance between one Landau level to another Landau level. That energy scale does not depend on the strength of the interaction between electrons. There is another energy scale, which is the distance, which is determined by the Coulomb repulsion between the electrons. So that energy scale is E squared divided by R, where R is the average distance from one electron to its neighbor. So the existence of a gap is important properties of the quantum Hall system. In the fractional quantum Hall state, we will consider a regime in which the distance B over m is much bigger than the gap itself. That regime can be realized theoretically by taking the limit m goes to 0. In experiments, you take the magnetic field to be very large to realize this limit. In this limit, since all the higher Landau levels has been pushed to infinite energy, all the interesting physics should happen on the lowest Landau level. So in this limit, this limit is the limit for which Laughlin wrote his famous trial wave function for the fractional quantum Hall state. It is a very simple ansatz for the wave function, and it seems to capture many important features of the quantum Hall effect. In this talk, I will tell you that there are some information that some important information that goes beyond the lowest, the ground state wave function. Of course, we know that the ground state wave function does not contain all the information about the system. We need to know the excited state about the system in order to, for example, compute the transport. So let us think about the electromagnetic response of a quantum Hall system. What happens if we put in electric field to the system? Since our system has a gap similar to insulators, then it would be useful to remind ourselves what is the theory that describes the electromagnetic response of insulators. For long wavelength and low frequency external electromagnetic fields, the effective action that describes the response of insulator would be characterized by just two numbers: the epsilon dielectric constant and magnetic permeability. In 2 + 1 dimension, there is one more term that one can write down. That is the Chern-Simons term in the action, and that term is what would correspond to the whole physics. So it encodes the whole conductivity. It's very easy to see. If we take this action is just an action in terms of the external field. So in order to compute the current, we just take the derivative of the action with respect to the gauge potential. And if in this formula we put mu equals 0, we would have rho, the density, equal nu over 2 pi times b. That identifies nu as the filling factor. That is the number, the ratio of the density, the number of electrons over the degeneracy factor of the Lewis-Landau level. And if we take nu to be a spatial index, then we would have sigma xy equal to nu over nu times the quantum conductivity. So it seems to be a very nice topological action that encodes the information about the quantum Hall physics. So many people believe that all universal properties of quantum Hall systems are encoded in the Chern-Simons action. Recently, we have found that there are some universal properties of quantum Hall, of certain quantum Hall state, namely clean, rotationally invariant quantum Hall states that goes beyond the Chern-Simons action. Let me show you one particular example. So let us imagine that we put a quantum Hall system in an electric field that varies in space. So E of x would be a function of x itself that varies with the wave number q. And then imagine that we can measure the local current that flows at each point in the system. The current will be Hall current perpendicular to the electric field, but as the electric field changes sign along the x direction, the current also changes sign. But the ratio between the current jy and ex determines the Hall conductivity as a function of the wave number q. For q equals 0, we know that sigma xy at q equals 0 is equal to the Hall conductivity, namely mu times the quantum of Hall conductivity. So we can expand for small q the sigma xy to Taylor series over q. And the expansion parameter, the natural expansion parameter, is q times L, where L is the only length scale determined in the problem, that is the magnetic length determined by the magnetic field. Basically, the radius of the circle through which there is one quantum flux going through. Now, the result that I'm going to derive, going to show you how to derive, is the relationship between the coefficient of the q squared term in this relation with the shift. So it turned out that not only the q to the 0 coefficient is universal, also the q squared, the next correction in q, is universal for quantum Hall state. And that coefficient is related to a topological property of the quantum Hall state. And this result is an exact result which is insensitive of the form of the Hamiltonian. It's robust toward small deformation of the Hamiltonian. So let me tell you a little bit about the shift. So let us consider a quantum Hall ground state on a closed manifold. So the manifold can be characterized by the genus. And if we write down the relationship between the number of electrons and the number of flux quanta in the system, in the thermodynamic limit, the number of electrons is equal to nu, the filling factor, times the number of flux quanta. However, there is an offset, a finite offset, that depends on the genus of our manifold. And the coefficient here the offset is proportional to 1 minus g times this coefficient s. G is a property of the manifold, and s is the property of the quantum Hall state. So, for example, for nu equal 1/3 quantum Hall state, this coefficient s is equal to 3, which can be derived by writing down the generalization of the Laplacian wave function on a sphere, for example. For nu equal 1/5, this s will equal 5, etc. So the relationship that we found here is a relationship between a dynamical quantity, the conductivity, with the topological property of the state. And we will find some relationship like that between a dynamic, where in one side of the equation we have dynamical information, on the other side of topological information. So how do we derive this relationship? So I will sketch the symmetry that allows us to derive similar relationships. So there is, we know that GR, the origin of general relativity, is a principle of equivalence, where if we have an observer in an accelerating frame, then effectively this observer will feel a gravitational field. So we can treat gravity with going to an accelerating frame. There is something similar in the system of electrons, non-relativistic electrons, all with the same charges and the same mass. So if we go to an accelerating frame, the electron feels a fictitious electric field that would create the acceleration. And in a rotating frame, electron feels a fictitious magnetic field. The Coriolis force in the rotating frame can be thought of as a Lorentz force created by a fictitious magnetic field. So that means that if we want, we can write down the theory of non-relativistic electron using any system of coordinates, not just inertial system of coordinates, but using any frame. So let us realize that at the level of the action of free electrons. So if I write down the second quantized action for free electrons coupled to external gauge field and external metric. So here we have both the minimal coupling and also a coupling that can be thought of as a coupling of electron spin through the magnetic moment to the magnetic field. All the electrons are fully polarized in this action. And then we can discover by trial and error two types of invariance. The first invariance is just gauge invariance, but there is a hidden invariance of that Lagrangian in which we change the frame. And the change of frame basically are those that leave time invariant and change space, coordinates only. And it's parameterized by parameter psi of k. And we can see that this is if we do these transformations, the action remains invariant. So what is interesting about these transformation laws is that we have a mixing between the gauge field and the metric. For example, in the transformation of AI, there is a gauge field Gij, and in the same with the transformation properties of A0. So here I'm writing this for one particular value of the G factor that is equal to 2. That turned out to be theoretically more interesting value.
But in general, there are gammas in that, in those transformation laws?
Yeah, this gamma here, instead of 1/2, we have gamma over 4. So for the question that we will be interested in, this gamma will not be important, but for theoretical treatment, it's gamma equal 2 is a nicer value. The origin of this transformation, so there are 2 points of view one can take on this transformation. we can say that these are just the invariants of the microscopic theory that we found out by trial and error, or we can try to justify it by thinking about relativistic origin of a similar symmetry. So imagine that we have a theory of scalars coupled to gravity, and then we take the non-relativistic limit. The non-relativistic limit is the limit in which we factor out the fast phase rotation of phi. But let us also imagine that the G00 and G0I component of the matrix have corrections of order 1 over c squared and 1 over c, like this. If we put the metric and the phi into this action and neglect all terms suppressed in powers of the speed of light, then we will find exactly the same microscopic action that we started out before, except that we don't have here the magnetic moment. Okay, so this is one way to see the invariance. But I would like to emphasize that we don't have to think about the relativistic theory at all. We can just start from the non-relativistic theory and then find out that there is invariance. Yes?
All particles have to have the same charge.
All particles will have the same charge. So these are all electrons in the, and they have the same charge and same mass. So,
why does the field psi shift under decomorphisms?
why should the field psi?
Yeah.
Oh, this is just a coordinate shift. So
Or just a local?
Yeah, just a coordinate shift. Okay, so now we can ask the following question. We wrote down the Chern-Simons action that involved the gauge potential A before, and we can ask the question whether that effective action is invariant under the transformations. And the answer is that it is not invariant. And we can see that explicitly by computing the variation of the Chern-Simons action when we get these two terms. Or we can just look at the transformation of A mu and notice that A mu doesn't transform anything like a one form. There are two terms that make it transforming not like a one form, and so the Chern-Simons action is not invariant. That is a very unusual situation. Usually we think about the Chern-Simons action as invariant over everything, but here, under this particular symmetry of the microscopic theory, the effective action is not invariant. So that means that we have we need to find out additional terms in the effective action that would compensate for the non-zero variation of the Chern-Simons action. Or, in other words, we have the chance to figure out universal physics beyond the Chern-Simons action from this symmetry. So in order to do that, let us formulate the requirements for the effective theory. The effective theory should respect general coordinate invariance, reproduce all topological properties of the quantum Hall state, and it has to have a regular limit in the limit when we take the mass to 0 and keeping the G factor equal 2. That is important because only in this limit the lowest Landau level has a 0 energy. And in this case, we are sure that the effective action is regular in the limit m goes to 0. From now on, we will put m equals 0 and gamma equal 2. So the mathematical tool that we use, so we have some invariance that doesn't look very nice. We need some tool to write down terms that are guaranteed by construction to be invariant under this symmetry. And this is the so-called Newton, one of these formalism is the so-called Newton-Cartan geometric formalism. Cartan, around 1933, wrote a couple of papers where he reformulated Newton's theory of gravity in a diffeomorphism invariant way. So he took Newton's gravity and rewrite it so that it looks like an Einstein gravity. At the end, it looks very similar. It's more complicated, but in form, it's very similar to Einstein gravity. So the geometry that we are dealing with here is very similar to the structure that Cartan is dealing with. The system we have does not live in a three-dimensional Riemann space. It lives in two-dimensional Riemann manifold at any time. There is a global time. So we can parallel transport a vector along equal time surface, but there is ambiguity of how to transport a vector from one time to another time. So in order to define parallel transport, we need to introduce another component to the geometric structure. Let me call that the velocity vector. So that velocity vector is something that connects one manifold to one point in the manifold at time t to another point at another manifold at time t plus delta t. So it's not a vector in the tangent space at given time. It is something that allows you to go from one time to another time. So the Newton-Cartan structure actually can be thought of as something composed of the metric at any given time and a vector that connect one time to another. So a nicer way to write the formulas is to introduce this n mu, these two degenerate metric, a covector and a vector in the structure. And there are because I'm running short of time, I will only tell you that this Newton-Cartan geometry allows us to define a natural connection in space that satisfies all the properties that a connection has to satisfy, even when the metric is degenerate.
So these things are functions of time?
These are all function of time and function of space. Yeah. So if we have V, then we can construct a gauge potential that transforms like a one form. So we can write the A tilde, the new improved gauge potential, in check that this gauge potential transform like one form. That means that if we now write a Chern-Simons term, we will find we will write down something gauge diffeomorphism invariant. Okay, so there are a lot more to that story, but let me just show you some result. So an effective field theory can be written down. It's actually more convenient to introduce several new auxiliary fields that are all massive, that you can integrate out and find. One of the fields is the Chern-Simons statistical gauge field, A mu. There is a parameter rho and V are, and then there is a Goldstone boson phi. If you have seen the composite boson theory of the quantum Hall effect, it is very similar to this is actually the Goldstone bosons of the composite boson, the phase of the composite boson. So A mu tilde is the improved gauge potential. This omega mu, I didn't talk about, but it is the spin connection of the Newton-Cartan space. So all these terms are universal, and there is some part of the action that cannot be fixed by the symmetry. So that part we will talk about it later. V, the velocity in the Newton-Cartan structure is determined by writing down the equation of motion. So A mu and the metric is fixed by the external probe, and V is determined by the equation of motion.
There's no kinetic term for V?
The kinetic term for V you can write down. Actually, it's something that I will show you how at the end how it will influence the.
It's not just a Lagrange multiplier.
V, if you ignore S0, it would be a Lagrange multiplier. So at low energies, actually, you can just take this upper line, and that would give you correct response to certain order in momentum expansion of the quantum Hall state. If you go to energies of order the gap, then you need this term. Okay, so sigma xy you can derive from this the sigma xy of the quantum Hall state, and you can also check by direct computation that for the integer quantum Hall state, the thing that we have derived is also correct. This check is important because all the things that we have said here up to this point does not depend on whether we are dealing with a fractional quantum Hall state or an integer quantum Hall state, and the consequence that we have derived should be valid even for nu equal 1. But for nu equal 1 state, we can explicitly compute sigma xy as function of q for at least for non-interacting electrons, and that allows us to check this formula. So we know that it is correct for the integer quantum Hall state, and the symmetry tell us that this formula will be valid for fractional quantum Hall state.
Where is the air dependence in the effective action?
Where is the
magnetic length in the action? Should I see magnetic length?
So it is in the external field. So you turn on an external magnetic field. So here, so you expand around the magnet. You have a background field, and that's where the magnetic length comes in. Okay, so if we want to describe the physics of the energy scale of the gap, then there is one. There are then things start to break rules, because you have a lot of new terms you can write down in the Lagrangian. These new terms are the terms that we collectively call S0 in this expression. But for a restricted set of external perturbations, namely unimodular transformation of the metric and those transformation of the gauge field that touches only A0, leaving the magnetic field constant, then we can write down effective field theory for small spatial momenta, but to all orders in frequency. For that, the effective field theory is parameterized by just two functions, and these two functions can be understood as the spectral density of the stress tensors, two components of the stress tensors. So in two dimensions, we have three independent components of stress tensor, which in the complex notation would be TZZ, TZ bar, Z bar, and TZ bar. So only TZZ and TZ bar are important for the effective field theory, and we can introduce two spectral densities. And these two spectral densities are related to two types of terms we can write down in effective field theories. So let us introduce this Kij, that is the covariant derivative of V combined with Gij, so that it transformed correctly under coordinate transformation. We can write down a series of K-square terms with all possible power of time derivatives. So all these would sum up. In order to sum up all these terms, we need one function, f of omega, an even function of omega. But in two dimensions, there is another type of term we can write out with the epsilon tensor, all that combined to another function of omega, g omega. And these spectral density of the stress tensor that we have introduced in the previous transparency are related to the imaginary part of these functions. And this relationship can be derived from using the effective field theory, taking this term into account.
This is the only structure from here?
In this, if we are interested only in the restricted set of external perturbation that we have here. If we change the magnetic field, there are more terms that we haven't classified, all these terms.
So that's independent of the kinetic term you put for V? Or?
No, these are the kinetic terms that we put
this
for V. Yeah, these are derivative of V square, for example.
Right.
Yeah. These are the only terms that we can write down for V. And the limit m goes to 0. So we take the limit on the mass of electron goes to 0. So from that we derive from this effective Lagrangian after computation and using dispersion relations, we can derive sum rules. These sum rules there are three sum rules, so two of them are written here. So the first sum rule is the sum rule that relate the difference between the two spectral density of TZZ and TZ bar Z bar with the shift. So again, here we have a relationship between dynamical information on one side. Basically, the dynamical information is the absorption rate, the absorption cross-section of gravitons with two different polarization by the quantum Hall state. and the shift of the ground state. The other one, very similar looking, some rule relates the sum of these two spectral density with something that is called the spectral, the structure factor. So the structure factor is defined by taking the Fourier transform of equal time correlator of density operator, subtracting from it some trivial contribution from higher Landau levels, and then divide the result by 1 over q to the 4th. So it turns out that if we subtract this structure, we will find that the remainder is proportional to q to the 4th, and the coefficient, let's call that S4. So from these two sum rules and the positivity of the spectral density, we derive the inequality S4 has to be bigger than something that is determined by the shift. Actually, it's the absolute value of S minus 1 over 8. This inequality actually was first proposed by Haldane in 2011, and we reproduced that inequality. What is interesting is that Laflin's wave function saturates the inequality. So there is something special about the Laughlin wave function, or the Hamiltonian, that give rise to the Laughlin wave function at the ground state, that one of the spectral density is exactly 0 at all frequencies. So there is one more spectral sum rule. This one has a different power of omega, but it requires a definition of something that we call the high frequency elastic modulus of the quantum Hall state. We have exact definition of this quantity in our last paper, and this relation, will give us some inequality on the relating the gap and the high frequency elastic modulus. So, and we can also build a model of the magnetorotons. The magnetorotons are neutral excitation in the fractional quantum Hall state that was experimentally observed in 1993 after being predicted by Gerwin McDonald and Pratzman. We can write down a model in which we have the only massive state is the magnetorotons, and in this model the function f and g are such. I'm sorry, this is not f and g, but one of the spectral density rho is equal to delta function, in the other rho is equal to 0, and that model saturates the inequalities. And it is a concrete realization of Haldane's idea that the magnetoroton is a fluctuation of internal metrics. Actually, the way we write down the model is that we introduce an internal metric of the Lagrangian coordinates of the fluid. So, because there is a lot of detail here, I'm just flash out this this slide, and you can find the details in our last paper. So let me conclude. The quantum Hall state live in a special type of geometric structure in which there is a global time, there is a metric, and Vi can be thought of as a Newton-Cartan structure. And we can, using this the symmetries of the theory, we can make physical prediction. We can compute Q-square correction to Hall conductivity, and the result is universal. We can derive some rules and inequality relating, in particular, dynamical information with topological information. And there are many open questions that need to be studied. The role of edge state, relationship with conformal field theories, the role of non-commutativity, and possibly holographic realizations of quantum Hall state. Thank you very much.
Questions? Anybody else?
I missed something. Is this
Yeah.
is this shift a topological invariant of the background? I mean, the way you wrote it, it sounded like it came from the spin connection times the velocity field.
Yes.
Is it topological?
Mm-hmm. So this one requires, sorry, this coefficient here, and so this omega mu is a U1 gauge field, so you have to couple omega mu to some current that is conserved. So that is a particle number current here.
Is someone in the front?
Yeah. So so you would check this. So experimentally, you would measure this spectral function and then check the sum rule. Is that what?
I think there is a certain. It's difficult to measure the response. So you don't have gravitons. You cannot scatter graviton physically to the system. So what you can do, I think, but it's only an approximation to the graviton, is to do Raman scattering. So you have you have photon coming in carrying one polarization. Sorry. So this has two indices. The spectral one electron that come in will carry one polarization, one index of this Tij, and the other photon going out, and the Raman scattering will carry another.
But that measures some combination of rho t plus rho bar, or what does that measure?
So if you choose the polarization of the photon, then you
directly measure
either one or the other.
And then you can just check the sum rule.
I doubt that you can check the sum rule because you don't have the same. The proportionality will between the Raman scattering amplitude and the spectral density will depend on the model, on microscopic computation. What you can try to see is that, for example, if the Lagrange wave function is a good approximation to the ground state, then one of the spectral density must be much bigger than the other, because we know for the Lagrange wave function the rho bar should be equal to 0, and so you can see that the Raman peak would be much more enhanced in one channel compared to the other. For example, that's what now it's more speculation.
Yeah, I mean, we know there are irrelevant corrections to the Chern-Simons action in quantum Hall, just like Maxwell terms. So in your Q-dependent subweighting correction to the conductivity, are those obviously suppressed compared to the universal term that you computed?
So there are terms like this. So the term that is universal. So the thing is that if you don't know the Newton-Cartan, this diffeomorphism invariance, you can say they are higher order derivative terms and they can have arbitrary coefficients. What turned out is that not all of them have arbitrary coefficients. Some of them have universal coefficients. So one of these terms would be E dot gradient of B divided by B. So now that the coefficient in front of this term is universal. You might be surprised that there is a B in the denominator, but it's not surprising. The gap in quantum Hall state itself is would go to 0 when you take the magnetic field to 0. And so B can stay in the denominator. So this coefficient here is the one that determines the E square. There is also E square coefficient. Actually, the coefficient in front of that term is also universal. It's proportional to m divided by B. In the limit m goes to 0, that term vanishes. And that is actually known under the fact that the coefficient has to be m divided by B is known under the name of Cohn's theorem.
So, I think Jan?
Yeah, sort of continuing on Holmes' question, just trying to get an idea of how it works. Right, so I had the impression that this shift is really related to a curvature of the embedding manifold. Right, so you take something like graphene, and I imagine that you have some kind of fluctuation of the curvature of the graphene lattice. Would that give rise to this kind of response?
Well, there are some. This prediction, for example, that we have here does not depend. It's completely a flat space statement. It does not depend. We source it with the curved space in intermediate state in our theoretical derivation. At the end, we put the space to flat and get the prediction for flat space. So it turns out that not all effective field theory that you write down in flat space can be lifted to a curved space and still preserve the diffeomorphism invariance. So that's how we can get the coefficient of that term. So to define the spectral density You can think about curved space, but you don't have to. You just say there are operators, the stress component of a stress tensor, and you define
But the next question maybe can be interpreted this way. Suppose if you do this experiment on the graphene, and then you may be able to deform the lattice structure of the graphene, then actually simulate those curvature, then you actually maybe can directly probe this effective action, and maybe to see the effect more directly.
Yeah. So if you look at this, it looks like the metric coupled to at least if you limit yourself to unimodular deformation, this Gij looks like just anisotropy in the band mass of the electron. So it looks like you can change that by deforming the lattice. But I think there is a subtlety here. I didn't talk about the interaction. Actually, in order to make the action with interaction invariant, you also have to make sure that the interaction term also deform coupled to the metric in a particular way. And that's what I don't know whether just deforming the lattice would satisfy that constraint.
Brian?
Yeah, so I was wondering about disorder. So you really need disorder to have the actual plateau. So how does that, I mean,
so here,
assume translation invariance, where does disorder come in?
So let me we assume the following. We assume that we are at the middle of the plateau. So we are having exactly the same number of electrons as the number of the field Landau levels. Now I don't completely understand the role of disorder. Then if we have if we take the so this result would be valid at the middle of the plateau in the limit when the density of disorder goes to 0. So now if we increase, you go to one side of the plateau, you start to have localized electrons. I don't know what are the corrections of this electron to this quantity.
Yeah. Is this correction applied also to the initial control?
Okay, so this result is valid for integer quantum Hall, s equal to 1 for the integer quantum Hall. So this is can be
so
verified. Shift is equal to 1. Yes.
So S, you still have a finite shift.
Yeah, it is just related to the degeneracy of the lowest Landau level on the sphere. So the number of state in the lowest Landau level is equal to n5 plus 1. When you solve the Schrodinger equation on the sphere, you find this extra 1 electron compared to that is S.
Yeah, in this image, basically it's a non-interacting problem. So is there any physical understanding why you would have such a correction?
Well, this is just a Q-square correction. So without thinking about the symmetry, the Q-square correction can have any coefficient you want. The way we think about that allows us to fix the coefficient. So I don't completely, well, there is a way I can interpret this result through the whole viscosity, but it is another story. Yeah.
Let's thank Thanh Son again.